Okay, let's start with a quick recap. So here is the Hamiltonian of the 5-4 theory that we are looking at. Okay, which we wrote as a sum of free part and an interacting part. Okay, and we wrote down the free part and an interacting part at time t naught. Right, independently, if you look at this piece, this is time dependent and that is time dependent, but the sum is time independent because the left hand side is, and that's what our H naught is. So it's basically the free part of the Hamiltonian evaluated at time t naught. Okay, similarly H interaction is the interaction term evaluated at time t naught. And we had introduced the fields in interaction picture, the phi i's and pi i's, which evolve according to free Hamiltonian. Okay, and you can also write the H naught as follows. So you can just sandwich it between these two operators. Okay, they commute. So because this is H naught, this is H naught, this will commute, and this kills this exponential. So H naught is equal to H naught. That's what you get. And if you take the H naught here, okay, and then from left and right you multiply with these two factors, and if you insert 1 in this form, okay, then you will be able to write H naught as follows. Sorry. Okay, so that's clear. Once you use this, you can convert all the phi's and pi's into phi i's and pi i's. And also you saw that the commutation relations that phi I and pi I satisfy are exactly the ones which free field operators satisfy. So these are equal time commutation relations. So fields commute at equal times. The same is true for pi. And the coordinate phi I and its conjugate momentum density pi I they have the usual commutation relation. Okay, and then we further use this to write down Green's functions or correlation functions in the full theory, which we write as follows. So these are basically the vacuum expectation values of time order products of a number of fields. Okay, and here omega is the vacuum of the full theory, the interacting theory. Okay, and the fields are in the full theory, and we saw that we could write it as follows. Okay. So the arguments of these fields phi i's are exactly the ones which you have here. And then you have this exponential factor. And this is free vacuum. And we should divide by the same quantity except for these fields. Okay, where this is the ground state of free theory, okay, and I have used that omega is normalized to unity, okay. So in the previous expression, in the previous time you had in the denominator this object, and that I have put to 1 now, okay. And for phi 4 theory, this object is the exponential here is this phi 4 theory. We have d tau, and then h comes with d cube x, or what am I writing? Let me write z instead of x, from minus infinity to infinity. So all the three space coordinates run from minus infinity to infinity, and the time coordinate runs from minus lambda to lambda, where lambda has a small imaginary part at infinity, okay. And then you have here phi right. This is correct, okay. Now I will use a shorthand. I will write this as integral d4z. So d cube z and d tau I will combine to d4z, but I will write these limits as minus lambda to lambda, okay. Just to remind ourselves that the time component has integration limits which are given by these ones, okay. So I write this as now lambda over 4 factorial, okay. So this is where we had stopped last time. So let me look at the numerator part here and the denominator part separately, okay. So denominator is easy, it's almost the same thing as numerator, except for the fact that phi I is with external points x1, x2, these are absent there, but it's the same thing. So let's start looking at the numerator. So we have here this okay. So what is this object? This sorry, I forgot the exponential, which I should not. I think factor of I is missing here. d4z phi I to the 4. Okay, that's what we want to calculate. So I will just expand this. Okay, this is an exponential, and you know what the meaning of this exponential is. See, this exponential is an exponential of an operator. Okay, this is an operator. The phi i's are operators, and this was formally defined as the expansion with so e to the operator a is 1 plus a plus half 1 over 2 factorial a square and so forth, right? That's how this object e to the a is defined. Okay, and we have already discussed about this one in detail. So I will just expand it and write as follows. So the first term of the exponential will be 1. So that's what I write here. So this is the first term you get. Then the second term comes with a factor of minus I lambda over 4 factorial. Okay. So it's let me see whether I want to write it differently. No, it's fine. So I write minus I lambda over 4 factorial, okay, and then you have one factor of this operator. So I get vacuum time order product of phi x1 up to phi xn, and then integral d4z phi I z to the 4th. Okay, so there are 4 factors of phi I in here. And similarly, if you proceed to nth term in this expansion, you get minus I lambda over 4 factorial raised to the power 4, 1 over n factorial, that comes because of the exponential. Okay, this is 1 over 2 factorial, 1 over 3 factorial for the next term, and so forth. And then you get this. Okay, I am forgetting to put I here. And now I will have such 4 terms repeated n times. Okay, so what I will do is I will write d4z1, and to save some space I will write d4z. I write like this. So integration limits are of course from minus lambda to lambda, and then you have phi I to the 4 z1, so and so forth, phi I to the 4 zn, and the vacuum, right, and it continues like this. So if we are interested in calculating these objects, the numerator, to some accuracy in lambda, let's say I am interested in calculating this object to order lambda, then I will just calculate the first term here and the second term. Okay, but if for some reason I am interested in going up to order lambda square, then I will calculate the first 3 terms, this one, and the next one. Okay, so it will be up to us up to which order we want to calculate our correlation functions. Okay, and accordingly we will get the results up to a certain precision. So our problem has boiled down to calculating these kinds of objects. Okay, which is apart from these integrals and some and some factors, it just expectation value of time order product of certain number of fields, in which some fields are at some space time points which you decide, you choose the external points x1, x2 and xn, and some others they are internal points, right? The z is not something you choose. So in the numerator, or look at this one. So here, this is what we are calculating, right? So x1, x2, xn, these are the ones which you choose, but you have no control over the z here, right? That's an integrated over thing. You do not have control over z. So such points I will call internal points. Okay, so let's try to calculate this. So what we will do is we'll look at the general object, this. Okay, here some of the xn's could be, some of the xi's could be internal points, they could be z. Okay, but this is a more general thing here. So if we can calculate this, we know how to calculate our Green's functions. Okay, so that's what we are going to do. And now we will use our framework of free theory, right? Because we have shown that our phi i's are exactly the free fields, so we can decompose them as before. So I will write d cube k over 2 pi 3 halves. Okay, and then we have a of k. Okay, it's exactly the same as we had before when we were looking at free field theory. Okay, I can always decompose in this manner. Here it's a 4 product. Okay. Now I'll do something. I recall that the A's kill the vacuum. So if you have A acting on vacuum like this, it kills it. Or if you take conjugate of this equation, then you have A dagger kills the vacuum on the left, okay, or vacuum in the bra form on the left, and A kills the vacuum in the ket form on the right. So this term kills the vacuum on the right, and this guy kills the vacuum on the left. So I will define 2 different objects, one containing only this and one containing only that one. So that's what I do. So I define phi I plus to be this piece. So you have integral d cube k over 2 pi 3 halves and a k, and phi I minus as d cube k over 2 pi 3 halves 1 over 2 omega k a dagger k e to the I k dot x. Okay, which means that if I take phi I plus and act on ground state, I get 0, and if I take phi I minus and act on ground state in the bra form, I get 0. Okay, so this is how I will write my phi I. So phi I, this operator is a sum of these 2 operators. Okay, so let's see how this is helpful, and for that I will first start looking at a 2-point function. Okay, we'll generalize to n-point function later, but let's look at this first. Okay, so I'm looking at this time order product. So let's say x1 naught is larger than x2 naught. Okay, in that case, this object, or in this case time order product of phi I x1 and phi I x2, okay, is just phi I x1, phi I x2, right? Because this one has a larger time, so it sits to the left, and this one has a smaller time, so this sits to the right. Okay, that's the definition of time order product. Good, then, so I write this object using phi I plus and phi I minus sorry, this is 2. Okay, so now I'll just multiply these. Remember, these are operators, so I cannot change the order. So if I multiply, I get the following. Okay, plus sorry, so this should be minus. Okay, plus phi I plus x1, phi I minus x2, plus phi I minus x1, phi I plus x2. Okay, Now eventually I want to put everything, sandwich this operator between the vacuum. Okay. So when I do that, look at this one. See, phi plus kills the vacuum to the right and phi minus to the left. So this one has a phi plus, it will kill the vacuum. This one has a phi plus, it will kill the vacuum. This one has a phi plus, it will kill the vacuum. Okay. This will kill the vacuum also because it has a phi minus on the left, either way. But this guy will not kill the vacuum, right? So this is something which will give some non-zero value. So what I will do is I will leave these three terms as it is, as they are, and interchange the order of phi minus and phi plus in this term. And for that I will just use commutation relation and write this as phi minus x2 phi plus x1, and then you have a commutator. Right. So now if you see, I have the following result. I have term number 1, term number 2, term number 3, term number 4, and term number 5, right? And in all the 4 terms, 1, 2, 3, 4, you have always a plus to the right and minus to the left. Okay. And of course, if you have both pluses, then it doesn't matter, because you see the pluses are what? Pluses are containing a's, and a's commute. So the order does not matter here. You can write whichever way you want. Okay. And but here the order matters. So anyway, we have eventually the 4 terms which kill the vacuum and 1 term which does not kill the vacuum, which is a commutator. Okay, and commutator is just a complex number, because this apart from the exponentials, they contain a's and a daggers, and that will give you a delta function. So together it forms a complex number, and that when you sandwich between the vacuum, it will just pull out that complex number, because that's not an operator, and the vacuum with itself will give you 1. Okay. So you get a number out of this when you sandwich between the vacuum. So what I do is I define before I define something, let me write the result for the case x20 greater than x10. Okay, and look at again the same object. And what would you get? You will get the same thing with x1, x2 interchange, right? But still the operators which kill the phi pluses will be on the right and phi minuses will be on the left, and the difference will come in this commutator piece. Okay. So you'll get exactly the 4 terms as before with x1, x2 interchanged, okay, plus this commutator, and the commutator will be this time x2 minus minus x1. I have to interchange 2 and 1. Okay. Now you see, when I sandwich the time ordered operator between the vacuum, okay, it will all these 4 terms will go away because they give 0, and the result will contain only this commutator and that commutator, and this commutator is present only when x1 naught is greater than x2 naught, and this commutator is present when x2 naught is greater than x1 naught. So let me write down the result. So the result will be the following. So first term was let's go back. Phi I plus hope it's correct, yes, and the one with the larger time argument phi I minus one with the smaller time argument. Okay, and this is the one which hits when you have x1 naught greater than x2 naught. Okay, so this is present only when x1 naught is greater than x2 naught. So that's what the unit step function is doing, plus the other term is present when x2 naught is bigger. So here you have phi I plus x2 phi I minus x1. Okay, that's the result. Okay, this is good. We have got some result for this expression, and I will now introduce a notation. So here you see the four pieces, 1, 2, 3, and this fourth, they were in a particular fashion which I told you. Okay, that the pluses are to the right and the minuses are to the left, and when operators are in this form, we say that they are normal ordered. Okay, so that's the definition of normal ordering, because, and this is useful because if you have a operator or operators which are normal order, and if you were to sandwich those between vacuum, you will get a zero result. Okay, so it's useful to define something called normal order, and the symbol is this. This is the symbol used for normal ordering. So if you have operators a k1 and a k n, so let's say you have a series of a's, and then you have another series of a daggers, and then maybe you again have another series of a's, okay, and so forth, maybe another series of a daggers. And if you were to normal order these operators, then what you get is the following. You should get a's to the right and a daggers to the left. So all the a's should appear on the right. So you'll get a of k1, a of kn, okay, keep forgetting this, and then you will have a q1, a qn, not n, I have used s. Okay, so all the a's here and all the a daggers here. Okay, and if there are more a daggers, you can put them here. Okay, and between a daggers, the order doesn't matter, right, because daggers commute, and between a's the order doesn't matter because they commute. So this is the definition of normal ordering. Okay, it just means push all the a's to the right and pull all a daggers to the left. Okay, that's what normal ordering means, and this is the symbol. Okay, so if you put between two dots all these operators, this is what you mean. Okay, now as I said, this is useful because the moment you put this between vacuum, that will give you 0. Okay, so let's see what it means. It means that the time ordered product of the fields phi I x1 and phi I x2, okay, that we had, we wrote it as the following. You write phi I x1, phi I x2. Okay, and remember phi I x1 and phi I x2 you can write as phi in terms of phi plus and phi minus, but then the four terms that you got, they were in a particular order, and now you can identify that they were in normal order. All the ones, all the pluses, see, plus contains what? Plus contains a, minus contains a dagger, right? So here all the four terms had a's to the right and a daggers to the left, right? So that's what we have here. We are saying that the time order product of these two fields is a sum of terms in which all the operators are normal ordered, plus a term which we got, which was this piece. Okay, and this I will denote by let me write it here. So I had the following. So I will introduce another notation. So I will say phi I x1, phi I x2. This symbol is read as phi I x1, phi I x2, and this is the contraction between these two. Okay. So this is the contraction between phi I x1, phi I x2, and what's the definition of this symbol? It's exactly this piece. Okay, what we got there. Okay, that's the definition of the symbol. So here I will write phi I x1, phi I x2, and I should take the contraction of these two. Right, so that's the result that I have proved. Now let's identify what this contraction is. Okay, and it is something we have already studied, and I will just quickly show you what that object is. So for that, recall that we had defined the Feynman propagator x prime minus x as theta of t prime minus t, and then vacuum expectation value of phi x prime, phi of x 0. Now I'll put I here because these are the ones which are evolving with free Hamiltonian. Okay, and phi I have reserved for interacting case, so I should write phi I, and t prime, sorry, t minus t prime I should write. Okay, so that was the definition of the Feynman propagator. You can go back and see. Now let's look at these quantities. See, this quantity is what? This is a phi plus and a phi minus. That is a phi plus and a phi minus. Most of it will kill the vacuum. Only one piece will survive. Okay, and that you can easily check that. Maybe I will leave it as an exercise. It's easy, so I don't want to do it. So you can check that if you take this okay, you just get phi I plus x prime commutator phi I x the minus phi I minus x. Okay, that's what you will get. Okay, and with this you can show that our contraction of phi I x, what was it, x1 phi I x2, this contraction is exactly df x prime x1 minus x2. Okay, so these are easy exercises to do, and with this we conclude that our time order product of two fields is just the normal product of these two fields, normal ordered product of these two fields, and a contraction, right? So let me write it. So we have proved that this is just normal ordered phi x1 phi x2 plus the Feynman propagator df x1 minus x2. Okay, or maybe I will leave it like this. Okay, where we know that this contraction is a propagator. Okay, so that's going to be very useful for us. So let's put a box around here. Okay, I'll give you another exercise in which you have to just follow the same steps which I have used for this 2-point function, and it's not difficult. So exercise, before I give the exercise, I will introduce a shorthand notation. Okay, what happened? Okay, so I will introduce a notation first. So instead of writing phi I x1, I will just write phi 1. Instead of writing phi I x2, I will just write phi 2. Okay, just for ease of notation, otherwise I will end up spending too much time. So use this and show the following, that if you take the time order product of 4 fields, okay, where I have used this shorthand, you should show that this is equal to the following: normal order product, so there will be normal ordering involved. Let me write like, okay, we'll finish at the end. So you have phi 1, phi 2, phi 3, phi 4. Okay, that's equivalent of what you got here. So you got just these two. In fact, this result I can write like this. I can write it as phi I x1, phi I x2 plus this contraction and put the normal ordering outside. Right, I can do so because this is just a complex number, right? So there is no meaning of ordering between this. This is just the propagator. There is no operator left in here. It's proportional to identity operator. So I can pull out this thing and put it here. Okay, the same thing. So in the case of with 4 fields, you will be able to show that you have this term plus phi 1, phi 2, phi 3, phi 4, and a contraction between phi 1 and phi 2, okay, plus, now instead of 1 getting contracted with 2, 1 will get contracted with 3. Okay. Now 1 will get contracted with 4. Then you have possibility of 2 getting contracted with 4, and then 2 could be contracted with 4, sorry, in this one 2 was contracted with 3, and this one is 2 with 4. Then you can have 3 contracted with 4, correct, plus 1 with 2 and 3 with 4. One with 3 and 2 with 4, one with 4 and 2 with 3, and this entire thing is normal ordered. So you see, you get one term which has all the 4 operators, then you get 6 terms, 1, 2, 3, 4, 5, 6, which have only 2 operators, right? This one has only phi 3 and phi 4 as operators, and this contraction is a complex number, right? That's the propagator. Similarly, this one has only 2 operators, phi 2 and phi 4, and this contraction gives you a propagator between x1 and x3. Okay, so these 6 contain 2 operators each, and these 3, they are fully contracted. So there is no operator left at all here. Okay, I think I have written wrongly. I should omit this. That's just the time order product. Okay, this is the result. Now you see that if you were to sandwich this time order product of these 4 fields between vacuum, this will go away, this will contribute to 0 because they will kill the vacuum because of normal ordering. So what I'm saying is, what I'm using is the following. So if you have a normal order of a sum of operators, okay, so let's say OIs are our sum operators, then this is just sum of the OIs in normal order. Okay, that's what I'm using. So I can take these normal orderings and put on the individual terms. Okay, so then when you take this in the normal order, then this will kill the vacuum on if you sandwich the vacuum on both the sides. Similarly, this one, and all the 6. But these ones, these are complex numbers and proportional to identity operator. Only these 3 will survive, right? So we have the result that 5, 2, 5, 3, 5, 4 in vacuum is just Phi 1, Phi 2 contraction and Phi 3, Phi 4 contraction. This and this, okay, where I have used the fact that this is equal to 1. Okay, so you see that our problem has now reduced to writing the time order product of several fields in terms of normal order. Okay, because once we do that, all we are left with is these contractions, which are nothing but the propagators, right? So if you wish, I can write it further as d of x1 minus x2 df of x3 minus x4 plus df of x1 minus x3 df of x2 minus x4 x1 minus x4 and df of x2 minus x3, right? It's the same thing as before. Now let me state the most general case. So it goes by the name Wick's theorem, and it states that if you take time order product of n number of fields, okay, then that can be written as a normal order okay, so this most general case can be written as the following. So you take all the fields phi I x1 up to phi I xn, just like in your case of 4 fields, plus you should do all possible contractions. Okay, just as we did here. So you have to construct all possible contractions, starting with only 1 contraction, then going to 2 contractions, then 3, 4, and so forth. Okay, and we'll prove this result in the next video. Okay, I'll provide the proof in the next video. Okay, so let's meet in the next video then.